Okay, so in this video, I'm going to show you how to use Stata to run simple regressions for continuous outcomes. And I say continuous outcomes, and you'll hear me reference that a few different times because if you have a binary outcome or a categorical outcome, you need to think about whether other methods are going to be appropriate, especially if you have a categorical outcome with more than two variables. So this is going to be assuming that you have a continuous outcome, and I'm going to show you how to run simple regressions with a continuous predictor or independent variable, as well as with a categorical predictor or independent variable. So to start with, you'll see that I have Stata already loaded, and I have a data set loaded into Stata as well. So this happens to be student level data in which every line is a separate student. And so let's say to start our first regression, let's say that we want to look at the relationship between race and actually not race. Well, let's look at the relationship between SES, socioeconomic status, and math scores. So in this case, what we want to do is start by thinking of what is our model? And by a model, meaning often it's represented by an equation, and this helps sort of formalize the relationships that we're thinking of. So in this case, we would be thinking of math achievement as our outcome or our dependent variable. And we would want to be thinking of SES, socioeconomic status, as our predictor or independent variable. And that becomes really important because if you need to put your independent variable in one place within the command and your dependent variable in another place. And if you mess that up, you're going to get results that don't actually answer the question that you're trying to work with. So starting off, well, let's look for, let's just say we're going to look at the relationship between math achievement and SES. So what we can do is just use the reg or regress command, and then we want to put the math score which is this variable right here. So put that first, and then so that's our outcome or dependent variable. That always comes first after the command. Then we want to include our independent variable or our predictor, and then we hit enter. And then the top panel of this gets us information about our model. So we've got number of observations that were used for the output that we've got below. What's the F statistics? So these are like model fit statistics. F, the p-value, which tells us whether our model is explaining a significant variation in the outcome. And we've got R squared, which we can convert to percentages. So this is a proportion. So we would say that SES explains about 19% of the variation in math scores. That's what this tells us. Then down here, we've got the coefficients that tell us more about the relationship between SES and math scores. So to visually show what that is, we could start by looking at just a simple scatter plot of these two. So we've got math score over here on the left, and we've got SES over here running on the x-axis. And so we can see that there is kind of an upward slope right here, but there's an awful lot of dots here, right? This tells us that the output from our regression tells us there's 21,000 dots on this scatter plot. And so what we could do is we could actually let's say that we want to reduce this to make it simple. What we can do is we can just have a line that summarizes the relationship here. So the line sort of takes the average of y for each value of x, and that's what we get. But let's say that we just want to get rid of the scatter plot. And let's say that we want to add a vertical line at 0. So this line that's in blue now, this is the same thing that we just saw in that scatter plot, just without now we don't have all the dots showing everything. So what we can do is go back and see how this all kind of comes together. So if you're used to, say, in algebra, y equals mx plus b is the equation for a straight line. That's what we're seeing right here. That's what these coefficients correspond to. So we'll start with the constant, which is the intercept, or the b in the equation of a line. So here the coefficient is 0.0049, so basically 0. So what that means is that when So looking at the the 0 line on our x-axis should correspond to basically 0 on our y-axis, which it does. Then what the coefficient here is, so this is the mx part of the equation for a line, and so the m is going to refer to a some sort of multiplier, and x is going to be the coefficient here. And so what we can do with that is say the standard interpretation here is for a 1 unit increase in SES predicts a 0.55 unit increase in math score. So what we can do is we can see how that corresponds to the visualization of this over here. So if we move to the right by 1 unit in SES, and here I'm saying unit because that oftentimes that's sort of the standard language that people are taught, but also because the way that these variables are constructed is really kind of in standard deviation units. But it's very important to make sure that your interpretation draws on the way that the variables are measured. So for instance, if your independent variable is a percentage, you would want to make sure that you're saying a 1% increase in whatever your independent variable is predicts a whatever change in your outcome variable. So just always use the scale of the variable. It's very important. But going back to our graph here, so if we move 1 unit to the right on our x-axis and we kind of move up here, we see that that the corresponding y value is around 0.5, just a little bit over that, because it would be about right here, which is the same as the coefficient here. And we could even extend that and say, well, what if we go 2 units to the right on our x-axis, on our socioeconomic independent variable? And we go up here, we'll see that the line crosses, that the corresponding value of y here when x equals 2 or SES equals 2 is 1.1-ish if we're just eyeballing it, which is the same as we're seeing here. It would be just a little bit under 1.1 if we're being very precise here. So that's what these numbers here mean and how they correspond to this line that represents the relationship between our independent variable on the x-axis and our dependent variable on the y-axis. Then if we look in our output over here, we can also see the p-value for each of these coefficients. So in the case of the constant, that is not statistically significant, but the p-value for the SES variable is less than 0.05, which in the social sciences is the level that we use. So this is statistically significant. And so we would conclude that there is a statistically significant relationship between SES and math score. And then if you want, there's other information in here too, like you can see the standard error of the coefficient, the t-statistic of that, of the relationship, the confidence interval, all that kind of stuff's here, but most people are going to look at the coefficient and the p-value. So that's how we look at how we do simple regression when we have a continuous outcome and a continuous predictor. Now let's say that we want to look at the same outcome. So let's say, but instead of looking at the relationship between SES or the extent to which SES predicts math achievement, now let's swap that out for gender. So we're going to use the same command, so the same regress command. We're going to put in the math score, and then I've got another variable here called female. In this case, female is a binary variable that in which a 0 represents male and 1 represents female. And what we want to do, because this is categorical, what we want to do is tell Stata that this is a categorical variable by including I dot. Now, in this case, because the variable is binary, you're going to get this. We'll get the same output whether we use I dot or not. But it's good practice to always put I dot in front of your categorical variables, because if you don't do that and it's a categorical variable that has more than 2 outcomes and they're not coded as 0, 1, you end up with coefficients that can kind of screw up your results. So always good practice to put I dot in front of your categorical predictors or independent variables. So what we have here is the output, as you can see, looks the same. Same number of observations used in the outcome. Same number of observations used to run this particular regression. But if we start looking down here, we see that this is not a great model because it's not explaining much variation in the outcome. So the R squared is very close to 0, very low F value, and it's not significant, which is not surprising given what we see down here, but we'll get there. So in this case, what we're looking at is whether gender or sex predicts a difference in math scores. So here, what becomes really important when you're working with this case, it's a binary categorical variable, is knowing how that variable is coded, or how it's measured, how it's represented in the data set, or what it represents. So in this case, because we have a binary predictor, what the constant means is this is less about the coefficient or the equation for a line, like when we had a continuous predictor or independent variable, and because this is really about mean differences, so differences in average. So because if I ran a scatter plot of this, we're going to get something that doesn't really make any sense, right? Because we only have values of 0 and 1 for our variable female. So we need to, because this relationship is different, we need to interpret it differently. So in this case, constant actually represents the average math score for males. So males are coded as 0, so they go down here into the constant. So on average, the math score for males is 0.03, and the math score for females relative to males is 0.007 higher. So again, very important to understand how your variables are coded so that you can interpret this correctly. Because again, this is, so what you would, if we were to interpret this, we would say that females relative to males have a math score that is 0.007 higher. And that difference, if we go to our p-value, is not statistically significant. It's very important that we say females relative to males, because if you said a 1 unit increase in female is associated with or predicts a 0.007 increase in math score, that doesn't make any sense, because can someone be twice as female in your data as someone else? And the answer is no, because of the way that that variable is coded. So this is really the same thing as if you did a t-test. So if, like for instance, if we did a conditional means table for this math variable, what we would get is the same information that we see up here. So like I said, the constant represents for males, so 0.031 relative to males. Females have a math score that's 0.007 and change higher. Same thing here, 0.007 and change higher. And then again, this difference is not statistically significant. So, and this is how we do a simple regression when we have again, we're working just with continuous outcomes or dependent variables, but we have a categorical independent variable or predictor. So that's how we would run a simple regression in that instance. And that's all there is to it.